All right, I'd like to thank everyone for tuning in to today's webinar. This is the sixth webinar in our 12 webinar series. Today's webinar is on how specifying CarbonCure in your parking lot concrete can lower your CO2 emissions. This webinar is being hosted by the Illinois Ready Mix Concrete Association. My name is Theron Tobalski. I'm the Assistant Executive Director. A few announcements before we get started. The Illinois Ready Mix Concrete Association website, www.irmca.org. You can click on the webinars tab. It'll list all 12 webinars. It'll have a description about the webinars, list the speakers, list their bios. There's read more option. All these webinars are being recorded. The recorded webinars will be posted on each of the individual webinar pages. On those pages, you can also register for the upcoming webinars that are coming up. Each of the webinars have sponsors that sponsor the webinar. Here you'll see a list of the sponsors for today's webinar. When you go on the IRMCA website, these sponsors have links to different information that they want you to read about. Some could be stories about different products or services that they have. So I advise you to go there and encourage you to look at the website and check out the links for the sponsors. With that, we'll get started. I'd like to introduce Allison Palmer, who is the Marketing Development Manager for CarbonCure Technologies, and Ryan Ciadella, who is our Vice President of Innovation and Market Development for Irmca. And with that, I'll turn it over to you, Allison.
Great. Give me 1 second to get my screen set up here. Perfect. So like Theron mentioned, my name is Allison Palmer. I'm the Midwest Market Development Manager for CarbonCure. Ryan, you want to give a quick hi before I jump in?
Sure. Ryan Ciadella from Ready Mix, oversee innovation and market development here at Irmca.
Perfect. So welcome everyone. Some of this may seem familiar to you if you've participated in a CarbonCure presentation before, but you may learn some things that you haven't heard today. I encourage you to put some questions in the chat that we can address at the end. And I look forward to our discussion after the presentation. And with that, I'll get started. And ask, did you know that the world's building stock is expected to double by the year 2060? That means we're building an entire New York City every month for the next 40 years. With all the new construction on the horizon, how will it impact the climate? When we talk about emissions in the built environment, typically it's operational carbon or the emissions released from powering the building. So think lighting, heating, cooling. And there's been some major advancements and initiatives put into place to reduce these emissions. Of that new construction I just mentioned, nearly 50% of the total life cycle carbon emissions will come from embodied carbon. So embodied carbon are the emissions released through manufacturing all of the products that are going into the building. Everything from extracting, refining, processing, and transporting these materials all have a carbon footprint. Between the years 2020 and 2050, the projected carbon emissions of new construction is expected to almost evenly be split between operational and embodied carbon. So that means there's some work to be done. Now, concrete is the most abundant man-made material on the planet. In fact, it's the second most abundant material on the planet after water. And because of its sheer volume, cement production accounts for about 7% of the world's CO2 emissions and is one of the largest contributors to embodied carbon in the built environment. Now, just touching briefly on the Embodied Carbon Challenge, this is a global emission alignment among architects, engineers, owners, and governments to achieve net zero carbon by 2050. So the SE 2050 stands for Structural Engineers 2050 Commitment Program, which is a response to the 2050 Challenge, which was issued in 2019. And the challenge just states that all structural engineers shall understand, reduce, and ultimately eliminate embodied carbon in their projects by 2050. If you're really interested in learning more and diving deeper into this topic, I recommend Carbon Leadership Forum as a great place to start. So how does CarbonCure fit into this picture of reducing embodied carbon? We've developed a technology that injects CO2, carbon dioxide, captured from industrial emitters into the concrete mix during mixing, just like an admixture. CO2 is stored in a big tank in a liquefied state, like the one in this picture. They're typically not that clean at our concrete plants, but for marketing purposes, we use a shiny one. But once introduced into the concrete mix, that CO2 chemically converts into a mineral and is permanently trapped into the concrete. This process actually improves the concrete strength, which allows us to optimize our mix designs. I'm going to talk a little bit more about the chemistry behind this throughout the presentation, but ultimately the message I want to come across today is the concrete being delivered to your job site meets the same performance criteria, but with a reduced carbon footprint. So CarbonCure is growing rapidly across North America. We're operating in over 300 concrete plants, been used in 9 million cubic yards of concrete, resulting in over 100,000 tons of CO2 saved. I really want to highlight here that we've partnered with a number of sized producers. It's not just for the big names. It's really meant to bring value to anyone who wants to see a carbon reduction in the environment that we're building in. So we have partners with as little as 5 plants, and then partners like Ozinga, which have over 100 plants. So everyone can realize the benefits of implementing CarbonCure. So walking through the process of how the technology works, starting with the CO2 supply. The CO2 is collected from large industrial sources like fertilizer or ethanol plants. CarbonCure does not capture the CO2. This is done by industrial gas suppliers like Praxair, Air Liquide, Airgas. These companies collect the CO2 from waste sources, purify it, and then resell it. But it turns out this is actually already a well-established market because it's the same CO2 that is in your carbonated beverages. So that means every time you're cracking open a can of soda or drinking a delicious beer, you're drinking CO2 that originated from a fertilizer plant. I know it sounds gross, but don't worry, it has been purified and is safe for consumption. But the important thing to note is that it really does nothing to combat our environmental problem, because once we open that can of soda, that CO2 is released back into the atmosphere as a gas. What we're doing here is tapping into that reliable food grade source of CO2, introducing it into the concrete, chemically converting it into a mineral and getting rid of it forever, even if the building is destroyed later on. So easy installation. Takes about a day and a half for us to install our technology with our concrete partners' plants. It's retrofitted onto their existing operations. So here the batching software is integrated with the concrete plant's central batch operations system. So this allows the automation of the optimal CO2 dosage into each mix. This dosage rate is found during initial testing and install, and the metering and injection of the CO2 is happening at the same time as other processes in the batching sequence. So there's no impact to the cycle time and therefore no impact to your construction schedules. This is a great representation of how the CO2 molecules look when injected into the mix. It almost looks like a dry ice or a snow. Naturally, a lot of people ask, is that going to have an impact on the temperature of the concrete? And the answer is no, simply because we aren't adding enough to make a difference. We're introducing about 1 pound of CO2 into every cubic yard of concrete, which is like 4,000 pounds of material. That 1 pound of CO2 just isn't going to have an impact on temperature. It'd be like throwing a handful of ice cubes into the back of a freight truck and expecting it to cool off. It's just not going to happen. So to understand our process of CO2 mineralization, I just need to do a 500-foot view of how cement is made. So cement starts by mining limestone, aka calcium carbonate from a quarry. We heat that up to about 2,600 degrees Fahrenheit, and that molecule actually splits in half. 1/2 becomes CO2, which is the waste byproduct. And as you can see, 1 ton of cement produced equals almost 1 ton of CO2 emitted. So a huge environmental impact here in the cement manufacturing process. The other half of that molecule becomes calcium oxide. This is the critical binding material needed to make cement. So then we ship our cement off to Ozinga, and they mix it with sand, aggregates, water, cement, other SCMs to form our concrete. And now this is where we come in. We're introducing that precise dose of CO2 into the mix during mixing, just like an admixture. It gets dispersed throughout the mix and warms up to room temperature as a gas. And as soon as that CO2 becomes a gas inside of the wet concrete mix, it's like a magnetic attraction that occurs between the CO2 and the calcium from the cement. These two molecules want to bind together and return to their original state of calcium carbonate, aka limestone. These reactions increase the overall strength of the mix and is a key element to the success of the CarbonCure technology. The CO2 will make your concrete stronger while allowing you to reduce your cement content by about 5 to 6%. Without impacting fresh or hardened properties. So the key to all of this is when these calcium carbonate molecules are created chemically inside of the concrete mix, they're super, super tiny, smaller than silica fume. These tiny nanoparticles will bind to the outside of the cement grains and increase the surface area of the cement, making the cement more efficient. About 0.2% of the cement is reacting with the CO2 to form these nanominerals, and the other 99.8% of the cement is continuing to undergo normal hydration, but with enhanced efficiency thanks to these nanominerals. Here we have an industrial trial average conducted over a number of studies. The two different bars are two different mix designs measured for strength for different dates after pouring. The lighter bar on the left is a typical concrete mix, sand, aggregate, water, cement. The orange bar is that same exact mix, but with CO2 mineralization. So as you can see, a very high initial onset of strength, which tapers off to about 10%. So we see an average compressive strength gain of up to 10% at 28 days. Measured for strength over the past 10 years. So we can conclude that the formation of calcium carbonate nanominerals improves the compressive strength of ready-mix concrete. Higher strength allows us to optimize our mix designs and reduce our cement content. So this is where the real value of the CarbonCure technology comes in, especially in relation to carbon savings. What we're looking at here is an example of a case study of a concrete mix that normally reaches about 4,000 PSI at 28 days. The light bar on the left is our control. The middle bar is that same exact mix, but with a 5% cut in cement. As you would expect, when you take out that cement content, you're going to see a drop in strength. The orange bar all the way to the right is the same mix with 5% cut in cement, but with CO2 added back in. So it brought the mix back up to where it was at about 4,000 PSI at 28 days. This is a really great example of an optimized mix. QC team works really closely with our technical services team to figure out how much they can adjust a certain mix and how much cement they can take out while maintaining the same historical strength. So the addition of CO2 and reduction of about 5% cement has no impact on the pressure hardened properties of the concrete. In fact, if we didn't tell you CO2 was being used, you would not be able to tell. It has the same set time, workability, pumpability, temperature, and finishing. No impact on air content and can be used with any admixture, aggregate, cement, or SCM. Hardened properties like freeze thaw, pH, density, durability, and color are also unaffected. And just to reiterate, CO2 has a neutral impact because there's very little of it, and we're just turning it into nano-sized limestone particles. And with that, I'm going to turn it over to Ryan to talk a little bit about durability.
Sure. Thanks, Allison. And as Allison mentioned, you wouldn't know the CO2 is in the concrete unless we even told you. When we were first approached about this technology, I'm paid to be skeptical. And, through all the tests and verification and everything that we've done, it's 100% accurate. You wouldn't even know it was there. None of the properties, the fresh properties, hardened properties are affected whatsoever. So there's been a variety of durability tests. Obviously everybody's concerned about freeze thaw and will this hold up, especially it being something new. But through various universities, different departments of transportations, third-party labs, and even a lot of the tests we've conducted ourselves internally have shown that there's neutral to even a slightly positive effect on the durability. And I can show you that on the next slide if you want to jump forward. So this is some actual local testing we did here in Chicago. CTL Group performed the tests as we proposed this technology to the Chicago Department of Transportation. Obviously, they wanted to see how well it worked, so we kind of went through the variety of tests that they required. So we did compressive strength, chloride ion penetrability, freeze thaw, and water-soluble chloride ions. And as you can see, the strengths, there's the two mixes on the far right. The 816Z CC is the mix with CarbonCure, and the mix directly to the right is the one without. As you can see, the strength obviously increased, as Allison mentioned, with taking even a cement reduction in that mix design. And then jumping over to the chloride ion, you can see that it's actually better than the standard mix, showing that the mix itself is more dense. And some of the reasoning we've been talking about that is just because of those nano-sized particles. The concrete matrix itself is denser, therefore not allowing as much to get through the matrix itself. And then obviously freeze thaw on par with the reference mix, and same for the water soluble chloride ions. So This test kind of paved the way for CDOT. They gave them the comfortability that they needed to actually approve this technology in a lot of their in-house work. And with this, they've poured, roughly, I think, 35,000 yards over the last couple of years using CarbonCure. And as we've seen, here, as you can see, there's other departments of transportation that are grabbing onto this. Some are even mandating its use. City of Honolulu is one of them. And then even locally, we've got some trials right now going on with the tollway here early this spring, as well as IDOT. So hopefully here in the next, 3 to 4 months, we'll be seeing this as an accepted technology for use in all DOT concrete.
Great. Thanks, Ryan. So how much CO2 can be saved? At the end of the day, this process reduces approximately 25 pounds of CO2 per cubic yard of concrete. This figure can vary quite a bit depending upon the mix design, but one way we see these reductions is through that 1 pound of CO2 that's injected into the mix, converted to a mineral and permanently sequestered. But the majority of the carbon savings really come from the ability to reduce our cement content. So if you recall, that 1 ton of CO2 of cement produced equals about 1 ton of CO2 emitted. So that's a huge impact. When we're able to reduce the cement content by about 5 to 6%, that's about 20 to 40 pounds of material, depending upon the mix. We can do an analysis on any given project if we know what mix design is being used and a rough estimate of cubic yards. But if you're doing any sort of back of the napkin math for some projects that are coming up, 25 pounds per cubic yard is a safe estimate to use. Just want to highlight some reference projects quickly. So CarbonCure has been used on a wide range of projects ranging from Canadian winters to Hawaiian summers. So starting at the top left, we have Halifax multi-sport arena. So the concrete here was used on the arena's ice surface. So we needed some polished concrete here. We achieved some superb results. San Francisco, LinkedIn used CarbonCure as a part of its low carbon concrete initiative, was featured on CNN and utilized by LinkedIn as a marketing campaign. So great marketing opportunities when you are using CarbonCure on some of your projects. The Wharf in Washington, DC, Chicago, Ozingo was our producer on this one, Advocate Hospital Edition, and you said Barrier 1 was actually used here for moisture mitigation. McDonald's used CarbonCure on its flagship restaurant to highlight the company's commitment to sustainability innovation. Again, Ozinga supplied this project. Georgia Aquarium in Atlanta used CarbonCure on all its applications, including the shark tank enclosures, which had a high exposure class due to the salt water. Hawaii DOT was the first to demonstrate CarbonCure for paving applications. And then in Calgary, CarbonCure was used for 33,000 cubic yards on its east de-icing apron facility for airplanes. And then, Ryan, you want to talk about some of your projects?
Sure. So, and as Allison mentioned on the previous slide, the ice arena is one of particular note, as well as the airport. Everybody knows airports are extremely stringent, high technical requirements, and it just goes to show that with the ice arena, with their high level of FF and FL numbers required, that interior applications are also very suitable as well as the harsh environment of a de-icing facility at an airport. So this is just one local project here that we've done recently. It was just over 7,000 yards of pavement. Running through some EPD calculations, the original design was roughly about 248 kilograms of CO2. Utilizing just CarbonCure, not even looking at any other additional SCMs, we were able to save roughly 113,000 kilograms of CO2 for this project alone. And then just some rough figures in terms of what that does. It's about 129 acres of forest absorbing CO2 for a year, and about 250,000 miles driven by the average passenger vehicle. So as you can see, just the incorporation of CO2 and allowing for that cement reduction, you can have a pretty big impact. And, again, as Allison mentioned, it's not just the incorporation of that 1 pound of CO2, it's really the cement reduction where the value really occurs and where you start to see some of the savings. And then just looking at some general, obviously part of this webinar is talking about parking lots and whatnot, and obviously some of these larger lots that we deal with are some of these, distribution warehouses. And just looking at some various sized projects that you would see, in this market and even in other markets, based on the size of the warehouse, you've got, for example, 500,000 square foot warehouse is roughly about 11,000 yards of concrete paving. And then that roughly translates, that 20 to 25 pound per yard savings to about, 218,000 kilograms of CO2. So, that's just for the outside. If you start to incorporate that on the inside, as I mentioned, those numbers, could double, if not, almost triple. So, and this is where also too, for some of these larger distribution facilities where they're concerned about their ESG rating, looking at the indirect scope 3 emissions, you're purchasing products that are coming from suppliers that are, sustainably trying to make a difference, trying to source products that have a lower carbon footprint. And again, just by looking at using CarbonCure for the cement reduction, outside of just the SCMs, you can have a pretty big impact here. And again, a lot of the questions we do get is, how do I write this in a spec? What can I do to allow this for use on my projects? A lot of people are concerned about single sourcing, but as you can see here, I've got a couple different options in here from live projects we've actually supplied to, and they just refer to it as carbon mineralization, CO2 mineralization. That's the basic process that Allison described. You can call out, CarbonCure specifically or an approved equal. So, realistically, just referencing, the carbon dioxide mineralization is really the key element here, as well as allowing for the reduction of the cement as it doesn't get hindered by any prescriptive specifications. Minimum cements, water cement ratios, those can be a little bit of a hindrance trying to make this work and to really achieve some of the carbon reduction goals that you're looking for.
Exactly. So like Ryan just mentioned, the biggest barrier that CarbonCure faces are prescriptive specifications. So oftentimes these result in unnecessary limitations to sustainability improvements. So prescriptive specs such as minimum cement contents and maximum supplementary cementitious contents are outdated practices that originated from a time ago when quality control standards were just not as robust as they are today. So these specs typically result in higher carbon impacts, higher costs, and believe it or not, sometimes lower quality concrete. So the NRMCA and the Structural Engineers Institute recommend removing these specs altogether and moving to a performance spec like strength. So how can you help reduce concrete's carbon impact? Communicate your commitment to embodied carbon reduction throughout the supply chain early and often. So much of the time, things just get lost in translation between owners and designers and builders that we all have the same goal of wanting to do good for the environment, and we're just not communicating that goal as often as we should be. Design strengths for what you need. Use supplementary cementitious materials like fly ash and slag. Consider innovation, low carbon cement when available. Consider recycled aggregates or high quality aggregates when available. Remove unnecessary prescriptive concrete specs and consider using performance-based specs instead. And ideally specify the use of carbon mineralized concrete whenever possible. And if that's not possible due to those competitive bidding requirements, we ask that you allow the use of carbon mineralized concrete in the event that we secure the job. So with that, I will ask, are you ready to build with CarbonCure? We really appreciate your time, and I'll open it up for questions.
Thanks, Allison and Ryan. Great job. We do have a question. Approximately what percentage of the CO2 introduced into the mix is converted into CaCO3, and what percentage escapes as CO2, if any?
Ryan, do you want to take this one? I'm not sure of your exact dosage rate here.
Yeah, so out of that rough pound, that we dose it with, I mean, it's roughly 85 to 90% is accounted for in converting into back into calcium carbonate. But when you start to do the calculations in terms of, the actual impact on the mix, that's taken into account on the back end as you're kind of doing the calculations as far as when it comes to EPDs.
Thanks, Ryan. And that's all the questions we have for today. I'd like to thank everybody for tuning into our webinar. I hope you enjoyed it. And as Allison and Ryan stated, we're here to be a resource to help you update your specifications to allow for CarbonCure and the other technologies that we're having webinars on. So don't hesitate to reach out and we could work with you on that. Our next webinar is on April 21st at 12 p.m. Central Standard Time. It's called Fibers in Concrete, the Benefits, Applications, and Dosage Rates. We have Larry Kaiser with GCP Applied Technologies and Matt Norman with Concrete Fiber Solutions as our presenters. Registration will open on Monday, April 12th. We also offer free engineering assistance. I'm not sure if you're aware of that, but we do have a bunch of engineers throughout the state that contact Irmca, and we help with any type of concrete technology that you're looking at, whether it's concrete parking lots or roller compacted concrete or pervious concrete. We just want you to know that we're a free resource to help you out. Also on LinkedIn, we advertise these webinars and we post and share technical articles and information. And then on Facebook and Instagram, we have IRMCA member spotlights. So we kind of let all of our members shine. You can see who they are, what they offer, and maybe some of these technologies they offer you want to incorporate into your specifications. And with that, I'd like to thank everybody again, and we'll see you on the 21st. Thanks.
Thank you.
Thank you.